So this follow-on video, which is going to be relatively short, is going to apply gradient descent, which we derived in general in the previous two presentations, and we'll apply it to linear regression, which is a good, simple test case. And this will round out our preliminary discussion of linear regression. So I reemphasize that gradient descent can apply to many other things besides linear regression, but linear regression is a good illustrative example. All right, so let's begin. All right, so remember how gradient descent works. If we have a cost function, j, we use that cost function and take the derivative. You can see the derivatives here. The derivative with respect to the first parameter and derivative with respect to the second parameter. And we update each parameter according to the derivative, right? The first parameter is updated in a direction that opposes the derivative. So that's in the direction of decreasing j. And we multiply by alpha to mitigate the effects or to control the effects. Sometimes alpha will be small, sometimes alpha will be large. And if you recall this picture, whether alpha is small or large really depends on the steepness of the bowl that corresponds to your penalty function, right? If you have a very steep bowl, then you want alpha to be, so alpha and the second derivative kind of have an inverse relationship, right? If you want more detail of that, you can go back to the previous video where I discussed that. All right, so this is our general algorithm. Now in our particular case, our j is a quadratic function of theta 0 and theta 1. Now, why do I call it a quadratic function? Well, you can see here that this is a sum of m terms, and each term is a square, and each square involves theta 0 and theta 1. Right? So if I square these terms, and you can do this exercise yourself, if I square just one of these terms, what type of terms would I obtain? Well, some terms would be proportional to theta 0 squared. There would be a single term that's proportional to theta 0 squared. There's also a term that's proportional to theta 1 squared. There's another term that's proportional to theta 0 times theta 1. And there's another term that's proportional to theta, another term that's proportional to theta 1, and finally another term that's constant. So that's if you write down all the expressions that I wrote, if you do that exercise and write out all these terms, what you'll get is the general quadratic function of two variables. It's a polynomial in two variables, and the highest degree is 2. So you have theta 0 squared terms, theta 1 squared terms, and theta 0, theta 1. So that's called a quadratic function of these two variables. Now, if you have more than two variables that you're trying to fit, it turns out that it's still a quadratic function, but it's a quadratic function in more variables. We'll get to that in part 2 of our discussion of linear regression. But at this point, here's our objective function, our penalty function, and we're writing it this way. If you recall, this 1 over 2m was kind of a freebie. I could put a 1 over 2m there or not. The minimum of this sum of squares is the same as if I multiply by a constant. And I illustrated that in an earlier video. Notice that 1 over m is kind of like the average. So you're taking half of the average of these sum of squares. All right, so let's move on. All right, so we need to evaluate these two derivatives. Now we have the explicit expression here, so we can actually take the derivatives. Remember how to take the derivative with respect to a single variable. Note this funny curly d here, that means it's a partial derivative. That means when I take the derivative with respect to theta 0, I treat theta 1 as a constant. So here I have 3 terms in here, and only the first term depends on theta 0. The other 2 terms would be considered as constants when I take the derivative with respect to theta 0. Now, since you're squaring this entire expression, you would need to use the chain rule. Right? So that's a nice exercise I suggest that you do that exercise. You take one of these terms, one of these squared terms, and evaluate the partial derivative with respect to theta 0 and the partial derivative with respect to theta 1. Okay. Again, I emphasize that when you take the derivative with respect to, say, theta 1, you treat theta 0 as a constant because it's a partial derivative. Okay. So those two expressions can be found explicitly. So we have the question marks here, so we're still in suspense, but you can do that calculation. I'm sure you can, and it will be very instructive. Right. So here's the general form that if I take the derivative with either one, with either theta 0 or theta 1, it's going to be the derivative of this sum. And here, of course, we're replacing the h with our explicit expression here. And here we're repeating our algorithm. So let's see what's going to happen now. Okay. So it turns out when you take the derivative with respect to theta 0, this is what you get. Actually, from the chain rule, you pull down a 2, and the 2 cancels this 2, and then you get this part. And again, if you want to get theta 1, if you use the chain rule, you're going to pull down a 2, and then here you have theta 1 times x. So when you differentiate this, again with respect to theta 1, you're going to pull down an x, right? But you should make sure that you know how to compute these partial derivatives. It's a straightforward calculus exercise. All right? So these are the explicit derivatives that we're going to use in these expressions. Okay? So here he has substituted explicitly the derivative of j with respect to theta 0. And here he has explicitly substituted the derivative of j with respect to theta 1. Right? So these are the equations we're going to use. We can put these directly into our computer because these are only algebraic operations. There are no derivatives here. Computers don't often know how to find derivatives. All right, so how would this apply to our particular data here? So this calculation goes through an exhaustive detail. So we can just, I'm not going to spend a lot of time going through each one of the steps. Here are the general equations here, and you can see the form here, how it works out. Suppose we start our theta 0, theta 1 with minus 0.2 and 1.1. So why did we start there? I don't know. It's just an arbitrary guess. Maybe you do some graphical analysis and suppose that this is fairly close to the right answer. Right? Now, given this initial guess and this data, we can compute these equations, right? If this is my initial guess, I start out with minus 0.2 for theta 0 on the right-hand side, and I start out with 1.1 for theta 1 on the right-hand side. Now, what are these xi's and yi's? Well, I runs from 1 to m, and here m is 3, because I have 3 data points. So this is x1, x2, x3, y1, y2, y3. Right? So if you plug in those values, you'll see that you get these formulas out. Just looking at the first one, to update theta 0, I start out, my initial theta 0 is minus 0.2, that's correct. And then I have minus alpha. If you look here, we're using alpha equals 0.1, so minus alpha. And then I'm times 1 over m. As I mentioned, m is the number of data points, which is 3. And then we plug in the 3 terms coming from the 3 data rows. First term, I'm going to have my theta 0, which is minus 0.2, plus theta 1 times x1. x1 is 460, and theta 1 was 1.1, so we get 1.1 times 460. And then here we subtract the first y, which is 6639. Okay, that's the first of these 3 terms. Second of these 3 terms, same theta 0, same theta 1, but the x and y has changed. I take the x and y from the second row. So you see the second row is identical to the first row, except that I've exchanged the x and the y. The third term in the sum uses the x and y from the third row. Okay? And then here you just work out this arithmetic and it turns out to get 384.34. Okay, so that's a big change in theta 0. I'm not sure why minus 0.2 was an initial guess. I think that's just out of the blue. In fact, with linear regression, no matter what initial guess you try, you will end up eventually with a correct answer. It will just take longer or shorter. And we'll talk about that in a couple of slides. All right, so that's how I would update theta 0. So is this the final value? No, that's just the next approximation, and we'll continue going on. Right. Now, how to update theta 1? Very similar. I'm going to use the second equation here. So I start out with my initial theta 1, which is 1.1, and here I have, then I'm going to subtract 0.1 over 3, and then I have these values here. So this is the initial value of theta 0 plus the initial value of theta 1 times the first value of x in the first row, value of y in the first row. So this discussion follows along just like the discussion for theta 0. Now there's a difference here because you need to multiply by x. Okay, so let's see. So this was time. So I multiplied here by x. So each term is multiplied by x. So this is multiplied by the first x, second x, third x. Work out the formula and you get this stuff, which looks quite big. In fact, this value is enormous, 117,000, when in fact the largest price in thousands is only 6,000. So what's going on here? What's gone wrong with our algorithm? Well, let's look back at our picture of the penalty function in 2 dimension. So this was our contour picture. Now we're starting at minus 1.1, and I'm sorry, starting at minus 0.2 for theta 0 and 1.1 for theta 1. That means we're approximately, let me turn this into a pen. That means we're starting approximately minus 0.2 right here. All right, now apparently the learning rate is of a size that the step is working out very, very large. And the direction is going to be perpendicular to this green line, so it's shooting way up. Well, that's not quite right. It's shooting way up. Let me erase the ink there. It's going to be perpendicular to that, so it's shooting way up into the stratosphere like this. And it's completely missing the actual point that we want. So in this case, the learning rate is way too big. So where do these big values for theta 1 come from? Let's go back to our particular expression with these particular numbers. Now when I computed these terms in my update expression, you can see that the biggest contribution to these terms is the y here times the x here. Right, this y term is quite a bit bigger than these other terms because these other terms are not doing a very good job at canceling the y term. So the reason that this is so big is that the y is big and the x is big. Now this kind of illustrates the point that you want to adjust your initial data so that it's expressed in good units. Right. These units are the hundreds, these units are thousands. Now, instead of expressing the size in square meters, I could express the size in units of 100 square meters. This would become 4.6, 0.7, 1.55. Those numbers are a lot smaller. I get lots smaller numbers in this expression. And instead of price in thousands of rand, rand is South African currency, I could express the price in millions of rand. And then these numbers would also be smaller. That's called scaling, and we'll get to that in a later presentation. But for now, I'm just making that point, that what you would really have to do in this case is greatly reduce the learning rate, and you do a lot better with your guess. But this guess is way out of the ballpark. I suspect that if we continued with this learning rate, the algorithm would bounce back and forth and probably diverge because the learning rate is just way too big. Okay, well, let's look at another example where the numbers are more reasonable. Right? All of these numbers are scaled to be between 0 and 10, And then these numbers are scaled to be between 0 and 20. And let's see what our learning rate, here we use a smaller learning rate. And you can go through this calculation. And here your first value of j, remember you're trying to reduce the value of j. So if I use this initial guess of 2 minus 0.1, and I plug that into my numbers here, remember how you plug this in, theta 0 would be 2, theta 1 would be minus 0.1, and the x's and the y's would come here. So you can work out this calculation. If you use this initial guess, your initial value of penalty function is 55.72. Now with this much smaller value of learning rate and these more reasonable numbers, work out the calculations. You get a new value of theta 0 is 2.1, the new value of theta 1 is 0.64. Work out the new penalty function and it's quite a bit smaller. Okay? So it looks like we're pretty much in the ballpark. We're doing pretty well. Now, gradient descent in general is going downhill, and we saw from this diagram that going downhill might not necessarily, let me go back there, might not necessarily take you to the very best point. It might not take you to the global minimum. You might end up in a local minimum. However, in linear regression, you only have one minimum, and that's a result of this so-called convex property. Convex, you can think of convex as meaning that the second derivative doesn't ever change sign. So the second derivative is kind of always positive, so we're getting this kind of bowl shape, convex shape, instead of concave shape. Right? So as long as your learning rate is not too crazy, it's always going to converge. Right? Now, if you're getting results where it doesn't converge, you reduce your learning rate, right? You're not going to increase your learning rate. So the starting point only affects how quickly it converges, but it will always go down. So you can see that downward is always pointing towards the center. In this case, the objective function is kind of circular, so it really doesn't matter where you start. You're always going to go basically straight towards the minimum. So we'll see other examples where things are not so nice. But it is true that gradient descent applied to linear regression will always converge, right, no matter where you start from. Right now, this kind of gradient descent is called batch gradient descent. Now, why is it called batch gradient descent? It's because you're actually using all of your data for each update. Right? To compute the next value of theta 0 and theta 1, I used all of my data. Now, it's possible, if you have a lot of data, you might update just using part of your data. And that would be called mini-batch. And what was the other kind called? And then stochastic gradient descent is another variety. And in stochastic gradient descent, instead of having m terms in this update, you'd only use one data row at a time for each update. So you can imagine you have to do a lot more updates when you use stochastic gradient descent. The difference between the different types, stochastic, mini-batch, or batch, just is how much of the data you use for each update. Okay. And I think that's the end of what we have for this part. All right, so thank you for watching, and we'll move on to part 2 next time.